So it's my pleasure to introduce the first speaker, Professor Prasad V. Bharatam. He's from Naipur, Mohali. He's going to talk to us on divalent cationic nitrogen species, chemical bonding, synthesis, and drug discovery. Of course, he has done a lot of work in the area of medicinal chemistry. So, Professor Bharatam, 15 minutes and 5 minutes for discussion.
Thank you, Professor Vijay Mohanan. I have chosen this title because many people are general science persons, and I would like to justify how quantum mechanics can be applied in drug discovery. In this lecture, we all know this equation, Schrodinger wave equation. The Hamiltonian operator, a molecular Hamiltonian operator is shown here. It is ferocious for some people, and it is easy for many people. This is kinetic energy due to all electrons, kinetic energy due to all nuclei, potential energy due to electron-nuclear repulsion, and potential energy due to electron-electron repulsion. Now, this is attraction, and this is repulsion, and this is nuclear things. If we understand, it is easy to go ahead. Now that we know this equation is very, very fundamental of all fundamentals, can we apply to drug molecules? This was a question we addressed in the last 25 years. I am addressing this question. And what we do with this, we study the electronic structure and chemical bonding in drug-like molecules. Employing Schrodinger equation, we can study electronic structure of drugs, chemical bonding in drugs, design new drug molecules with desired medicinal chemistry properties. This was a challenge given to me some time ago, and that's what I have been practicing. What we need for compounds of medicinal interest. Very first thing is that they should be mildly reactive. If they are chemicals with high reactivity, very good electrophilicity and electrophilicity, they may be giving unwanted reactions inside the body. So this is one thing is most important is mild reactivity. Next thing is there should be a proper balance between hydrophilicity and hydrophobicity, such that these molecules can penetrate through the cell walls and have a proper pharmacokinetics, and they finally reach the target of the choice. And then they should have the option for metabolism. If they are these genobiotics, when they enter into the body, if they get out of the body after they doing the drug action, it is going to be dangerous. So they should have a proper mechanism for metabolism and excretion. These are the main properties for chemicals. Can we design compounds with these properties with the help of quantum chemistry? This was the question. So this is what we looked at. The very first project I took up in my institute called NIPER, National Institute for Pharmaceutical Education and Research, is on this topic. This is bigonides. Most of the elderly people here probably have utilized a molecule of bigonide, that is metformin today. I took myself 1 gram of metformin today morning. So metformin is this topic, this compound. When we look at the neutral metformin, it is a beautiful molecule, intramolecular hydrogen bond, several external hydrogen bonds possible, very nicely understood. But it is not a drug. Metformin is not a drug. Metformin hydrochloride is a drug. There is a difference between these two. Metformin hydrochloride, when I look at it, it is a protonated form of the metformin. When we did the computational analysis on this, we realized that this bond, CN bond, can be better represented by a carbon-nitrogen coordination bond. This was a surprise for us in 2005. We kept it under the carpets for 5 years. In 2009, by 2009, we got sufficient confidence, and we declared that this is a carbon-nitrogen coordination bond, but not a covalent bond. Which nitrogen coordination bond, internal. Why? This particular species, diaminocarbene, is a carbene. donate. And nitrogen is plus charged, electron deficient, it can accept. This is same cyclic carbene can donate to nitrogen center. This was the idea. We continued this idea and we designed many compounds with this NHC carbon or NHC nitrogen coordination bond. Now in the literature there are so many species available with this particular bonding, a ligand donating to main group element. Here this series of compounds are known as carbones, these are borylones, these are silylones, germylones, stannilones, nitriones, phosphylones, arsine. Out of all of them, only these compounds can be drugs. All others are highly reactive. They cannot show drug action. Only these species, nitriones, can show drug action. That's what we focused on that. And then what are these nitriones? They are divalent N1 compounds. They are isoelectronic to carbones. Bi-coordinated nitrogen center is available. Datively bonded to two lone pairs at that donating ligand. These two, one donating, another donating. Both are donating to the central nitrogen. This nitrogen carries two lone pairs again, just like oxygen in water. So if that is true, can we design and synthesize many? This is what was the purpose. We synthesized many of these compounds. Some of them are open chain nitriones, some of them are cyclic nitriones. Several of these compounds are available now. In the last 15 years, many compounds became available. Having said that, where is medicinal chemistry? These compounds, when we look at the literature, we realize that nitriones are known, they are not new to the medicinal chemistry community. Anti-diabetic metformin carries nitrione character. Anti-malarial, cycloguanyl and proguanyl. Proguanyl gets converted to cycloguanyl. This metabolite compound. Antiseptic compound, chlorhexidine. This is a part of our toothpaste every day. The blue colored toothpaste contains chlorhexidine. We are utilizing this compound with coordination bond between carbon and nitrogen. H2 receptor antagonist, antiparasitic compounds, antiviral compounds. Several compounds are already known to be nitriones. So taking this as a membered ligand, 5-membered electron donating ligand, and another 4-membered electron donating ligand, we could synthesize this. And then we could get the crystal structure also. Then we have this compound where on one side we have remote N-heterocyclic carbene donating to the nitrogen center, and we got the crystal structure of that. Then we got these abnormal N-heterocyclic carbenes donating to the central nitrogen, and we got the crystals of these compounds. All this work was after performing the quantum chemistry. Professor Gadre is here. We have density functional theory. Today morning also Dr. Kalyan Raman mentioned about that. So we learned from him and we started utilizing all these techniques to perform synthesis and crystallize the compounds and get to the compound. Once we have the compounds, what do we do with this? We use in drug design. We use in drug metabolism. We study their drug delivery properties. We study their drug toxicity properties. And then the absorption, distribution, excretion. In pharmaceutical sciences, we can study all branches of pharmaceutical sciences with the help of quantum chemistry and fundamentals of physics. That's what we could establish. In addition to these quantum chemical approaches, we also utilize these tools like QACR, quantitative structure activity relationship, pharmacophore mapping, molecular docking, de novo design, molecular dynamics, virtual screening, and all sorts of technologies we could adopt, and we integrate all possible computational approaches, including artificial intelligence, for the purpose of designing. Then we enter into the lab. We realize that if we design a compound and there is no respect for that, there is no sufficient respect, and if we don't put it to practice, we have to get the compound in hand. Then our institute, my institute has helped me telling that why don't you do synthesis yourself? Yes, why not? That's what I did, and our lab students worked hard, and they got. In the same process, we got a series of compounds like this. These compounds, if I have a carbon with a lone pair carbene, it should be very anti-aromatic. If I can replace this R group with a ligand, I can design many compounds which will have 6 pi electrons, because this ligand can contribute 2 electrons to the central ring, and this becomes a 6 pi electron system. Taking this as a concept, we further designed many, it could be proven with the help of Nix values. These 4 pi electron systems, all of them carry positive Nix 1 value, whereas when they become aromatic, they become Nix value becomes negative. Especially for the nitrions, it is very, very practically aromatic. So as a result, we thought that why don't we go ahead and synthesize these compounds. These plots clearly show that anti-aromatic compound should show this inverse anti-clockwise rotation of the electron density, and whereas this according to a plot called IAScid plot, we can show that indeed our compound can become aromatic. This is all theory. Then can we design many more? Yes, we did that. And then can we synthesize them? Yes, we started with an aldehyde, we converted it into, we protected this first, and then we introduced another aldehyde on the other side, we got a dialdehyde here. This is a pyrrole dialdehyde, very simple compound. But if I can condense with this particular unit, I will get this kind of a simple organic compound with pyrrole derivative. I treat this pyrrole derivative with methyl iodide to convert into the corresponding here carbene here, 2 carbenes, and then the central unit becomes aromatic. So that is how we synthesize these compounds, and we could obtain them in the crystal form. This is a recent work of 2025. Taking kind of clues, we went ahead and we did lots of synthesis. Then we had to do medicinal chemistry. These are all the compounds we synthesized in one series, and we submitted them for biological activity. This antibacterial activity became apparent for this compound with MIC value of 3 microgram per ml. This compound TTMB showed 3 microgram per ml for pneumonia, and then for subtilis it showed 2 microgram per ml. We have better results in other bacteria also. Then we took another compound of the same series and submitted for anti-cancer activity. Tubulin inhibition was observed with, this is the data, 7.4 micromolar activity was shown by this compound. So finally, I would like to conclude that using the quantum chemical methods, we can design many compounds of this type as well as this type, and go to the lab and synthesize them and perform the biological activity to get to anti-cancer, antiviral of activities. So it is time for me to conclude that the applications of quantum mechanics proliferated into every sub-branch of pharmaceutical sciences. It can be efficiently employed in drug discovery. And then at NIPER Mohali, we were able to obtain compounds, and several patents are available, and a few compounds are very promising, which I am not yet revealing here. I don't have permission for that. Anti-cancer, anti-diabetic, anti-malarial, antibacterial, in all these branches, we could contribute. This is a team which is helping me.
Thank Dr. Bharatam for his very interesting presentation. We can have a couple of questions. Yes.
How many of these drugs eventually make it to solving a problem of, let's Let's say.
Our institute, we have,
Because they have to go
we can
clinical
go up to
tests and
patent publication. We do in vitro analysis or patent. Beyond that is not a
Somebody else
capacity
has to
of
take
our
it up.
institute
Okay.
at this stage.
Metformin hydrochloride is used for type 2 diabetes, then what was the need to develop this together with the eugliptidine? How does eugliptidine changes the chemistry of metformin?
Metformin drug action is not known. Metformin is showing decreasing the glucose levels, but how it is actually we don't know.
Because the other question that I had, and I still posing, is that which is the preferred target organ in the human body when metformin is taken together with the eugliptidine?
Eugliptidine GLP inhibitor, there are there's some details, biology, everything is available. That is taken in milligrams, but whereas metformin is taken in 500
No, that's not my
milligrams.
question. I'm sorry if I properly.
Right.
Which is the body organ where this molecule goes and hit?
That metformin, there is no answer for that.
There is no answer. Okay,
Answer
thank you
yet-
so much.
yet now.
Thank you, Doctor. Thank you.
Yes, Professor Gadri.
There are some proposals, but they are all not concrete proposals.
Yeah. Bharatam, DFT is adequate for your studies with simple function? Or do you find sometime,
If we always compare with all functionals, we find B3 631 is most suited,
okay, and,
more than all the complicated ones.
and the cheapest?
Yes,
possible.
cheapest for all properties, it is best.
I also have a question. 1 gram isn't too high? Normally, metformin, 500
Metformin is not
milligrams
dangerous.
It's not
It
dangerous.
is a prophylactic type.
But some renal toxicity, I mean, it has been reported. I don't know whether.
No, it is not dangerous. Some acidosis, it creates some gases. That it is not dangerous for 99% of the citizens.
Okay. So let us thank Dr. Bharatam for his very interesting presentation.